We are live, we can start.
Hello. Hi. Can you all hear me? Oh, I lost you. Looks good.
Yes, Mr. Can you can go ahead. We can all hear you.
Can you hear me? Oh, good
Yeah,
to
we
go.
can.
Okay, excellent.
Yeah.
Perfect. Okay, let me just share my screen. One sec. And I just need someone to tell me if you can see my slides. Yes or no?
Yes.
Beautiful. Okay. All right. Well, if it's okay to get started, I'm going to talk today a bit about end-to-end encryption. And by the way, I really enjoyed that last talk. I didn't see the entire thing, but it was really, really interesting. And I'm actually curious about the iMessage question. I'm going to talk today about end-to-end encryption and give a very high level, not terribly deep and technical state of the technical and the policy debate about end-to-end encryption. I should introduce myself. Let me actually do that on the next slide. I'm a cryptography professor at Johns Hopkins University. I've been working on this particular issue, end-to-end encryption and sort of the policy and the tech issues around this in the United States, obviously, for about 10 years. And of course, this is a problem that has a huge international component. And I'm going to confess right up front that obviously my viewpoint is very United States centric, and I only have a very much more limited idea of what's happening overseas. I will qualify that several times. I'm a co-author of a technical and policy document that came out in 2015, I believe. It's called Keys Under Doormats. And what it really is kind of a position paper that says, here is why you should not include backdoors in end-to-end encryption. And it's a really good document. I will confess that the lion's share of the work was by my co-authors, but my very, very distinguished co-authors who include people like Ron Rivest and Whit Diffie and Susan Landau and so on. I've been involved in a number of things on the edges, and I just want to list these. Not all of these are academic work, but they're things that I am happy I got to be part of. So this last year during the pandemic, somebody came to me, it was Alex Stamos, came to me and said, we need to fix Zoom. And so this is so relevant because we're here on Zoom. We need to add encryption to Zoom. We need to make Zoom more secure. And so I sat down with this really great team and we built a system to add end-to-end encryption to Zoom. A few years before that, I was involved in a project, heard Apple iMessage mentioned. So I was involved in a project that found vulnerabilities in iMessage encryption. I have great stories of trying to interface with the Apple team about that. At some point, I think it was in 2016, I was invited to Facebook to look over their new end-to-end encryption system called Secret Conversations. And a few years before that, I was very fortunate to be involved in some of the Snowden leaks and the reporting on that, mostly around how encryption was being compromised by the US government. And that was a fascinating time. We learned a lot. I'm pretty sad that we didn't take a lot of durable lessons away from what happened there, but I think the lessons of what governments can do when they want to compromise encryption is something that we need to remember. Good. Okay, so today I'm not going to talk about all those things. I'm mostly going to talk about the history of end-to-end encryption and what we call the crypto wars. And the crypto wars is kind of a shorthand, which many of you are familiar with, for how governments have tried to tackle open encryption systems and make them more tractable and more secure more available, more data available to them, or to prevent the deployment of cryptography. I'm going to talk about some technical details, including weaknesses and open research areas, but mostly this is a policy talk, and it's intended for people who have not been following the debate very closely. So those of you who have been following the debate will find it a little repetitive, but hopefully you'll learn something new along the way. And of course, like I said, it's a very US-centric talk. That's just where I live. I spend time talking to policymakers in Washington, D.C. I know how they think. I would love to learn more about how people in India think, and I would love to know more about how this debate is moving globally. I just don't have as much access to it. So it's not a US debate. All right, I'd like to start this talk by going back in time. I want to go back to the 1990s. These folks who you see on these slides, they're pretty well known. Some of them are pretty well known, at least. That's Phil Zimmermann, the inventor of PGP, at least back in the 1990s. That's Dorothy Denning on the right. She did a great deal of work around key escrow and how to deal with the Clipper chip. The folks in the middle, this is not actually a picture from the 1990s. This is the OpenSSL team. OpenSSL being a very relevant part of the crypto wars and the development of crypto in the 1990s. So going back in time, back to this 1990s period, was really an interesting time. So if you think back to the 1970s, we got the first public block ciphers like the data encryption standard. In the 1980s, academics began to really develop open public key crypto and do interesting things with it. That was the development of zero knowledge and all sorts of powerful crypto primitives. But it wasn't until the 1990s that public open source software to do useful things with cryptography actually came out. And the most famous of those programs came out in 1991. It was called Pretty Good Privacy, or PGP. It was written by Phil Zimmermann. And there's a story behind that of what inspired Phil Zimmermann to write this software, and I'll come back to that in a moment. But what you should know about PGP, if you don't already know about PGP, is it was the first piece of PC software that lets you take advantage of public key crypto. The 1991 version was pretty awful, but it was cryptanalyzed and improved and became something that was very powerful. There are other things that happened in the 1990s. There were DES challenges, so people started caring more about crypto. In 1994, something very important that's not end-to-end encryption related, something very important happened, which is that the first version of the SSL protocol was released by Netscape Communications, which suddenly made encryption into something the industry required, as opposed to something that open source advocates cared about. And in 1996, new crypto libraries were put out. In 1998, OpenSSL came out. That's kind of the history of what was happening in the 1990s. Governments did not handle all of this well, or at least the US government did not handle all of this well. And part of the reason is that historically, encryption and cryptography had been a subject for government agencies. It was highly regulated. Exporting cryptography was actually illegal, or at least you required a license to do this, and it was very difficult to get one. Now, how can you prevent somebody from exporting cryptography? Cryptography is a bunch of mathematical equations and maybe some software. And of course, in the US, that's very, very close to speech, and we have a First Amendment that says you can't block this. However, the reason this was so easy to do is because cryptographic knowledge was not very widespread, and because a lot of cryptography in the pre-1990s period involved hardware. So when you talk about exporting cryptography, typically you meant exporting some physical device. All of a sudden in the 1990s, exporting cryptography meant exporting a program. And we had a brief, very strange period where the US government tried to regulate the export of web browsers that had SSL capability. And you probably remember those times, if you were alive then, where there was a 40-bit international version of the browser and a 128-bit US version of the browser. And the way that you would decide which one you got was your IP address, which was hilariously stupid. And of course, anybody overseas could still get access to the strong one if they wanted. This led to all sorts of problems that mostly we cleaned up, but they lasted for many years beyond this. And this all kind of culminated in a period in the 1990s that we call the first crypto wars. Crypto wars is kind of a colloquial term, but basically the idea is in the United States, we had these laws, and these laws prevented the export of crypto. And of course, national security agencies wanted to maintain some kind of monopoly on crypto and the ability to cryptanalyze people's messages. In the 1990s, of course, PGP and other software just threw that out the window. It was no longer possible to do. There was this tipping point where suddenly governments had to face up to the fact that, criminals could download encryption software that was more powerful than their technology could break. And so they tried to come up with some kind of compromise. Very famously in 1993, the US government, with the help of the National Security Agency, developed a piece of hardware called the Clipper chip. The Clipper chip was a key escrow technology that said, it was for phone calls, that said every time you make a phone call, your phone call can be encrypted if you have this chip. But of course, most critically, the chip would also send a copy of the encryption key along with the message. And that copy was encrypted under a master key, which was stored, split across 2 US government agencies. And the folks at the NSA thought this was a great solution. Now we could have encryption, so businesses could make encrypted phone calls. But of course, the government, when they needed to, could come with a warrant and they could decrypt those calls. It didn't work. The system turned out to be broken for a variety of different reasons. But more importantly, the idea that we could replace software with these hardware chips was just not viable. And it turned out that if we had adopted that system, it would have pretty much slowed down the development of industrial crypto by many years. And so we pretty much abandoned that, mostly for very good reasons, even leaving aside the privacy issues. And at the end of the day, the result was primarily that we kind of moved on to a new regime. I want to show you this picture. Many of you will recognize this gentleman here on my left, the one holding the pen in his hand. This person was a very important figure back then, and actually he proposed some legislative language in Senate Bill 266 during this entire debate that basically demanded that telcos and maybe ISPs and so on include technology that would have forced them to reveal the plain text contents of voice, data, and other communications when appropriately authorized by law. And this was a piece of text that would have actually mandated the inclusion of either key escrow technology or no end-to-end encryption inside of these, inside of any communication technologies. And fortunately, for a number of reasons, this language was not passed into law. It was removed from the bill, but it gives you a sense maybe of where things were back then and maybe where things will go again, at least here in the US. Okay, so we can sort of report the result. Back in the 1990s, many people said, well, we won the crypto wars, we being the technologists and the pro-encryption advocates. And the result was that export regulations were not repealed, but they were relaxed, and open source crypto in particular was given a kind of an exception. If you write some piece of software and release it on GitHub, you do not need to apply for ITAR or export licenses. National escrow proposals like Clipper were just abandoned. And even better, our national laws, there's a law called the Communications, oh gosh, I can't remember it, Access for Law Enforcement something called CALIA, currently does have a provision that says you must turn over encryption keys or decrypt content if it's encrypted in a cellular provider or an ISP or a telco's network. However, the exception on this is only necessary if the provider themselves has access to the keys. So in other words, the current law as of today in the United States is if somebody uses end-to-end encryption on an ISP or a telco, and the telco doesn't have access to the key, which they shouldn't, then there's no need for them to do anything. And this applies to telecommunications companies and potentially to companies like Apple and WhatsApp and so on. So there is currently no law that allows the US government to force you to decrypt end-to-end encrypted communications. And that's a big deal. Okay, well, the great thing about the crypto wars is that, quote unquote, we won. The bad thing is at the end of the crypto wars, which is the late 1990s, nobody was using end-to-end encryption. And nobody is a relative term. Some people were using PGP. There were key signing parties and so on, but the usage was very minimal. So I guess the government decided, well, we can make an exception here because there's no threat. Nobody is using this technology. It doesn't really make our lives harder. In the 2000s, things got more interesting. Things began to change. And so what happened, of course, and I think you can sort of look and see what's going to happen based on the group of people that I've chosen here, is that technologies began to come online that made encrypted, end-to-end encrypted messaging, end-to-end encryption in general, something that was feasible. I'm choosing to begin this in 2004. Goldberg and Borisov developed this piece of software, not widely used, but slightly more widely used, that was called off-the-record messaging, or OTR. And OTR by itself, it never reached mass adoption, but it ended up being used on instant messaging protocols like AOL Instant Messenger and Jabber, and I think IRC. And I'm citing it here only because it really introduced two new concepts that I consider to be kind of the basis of our modern encrypted messaging infrastructure. And one was this idea of message deniability, that people who are using the system should not have their messages signed so that it's easy for somebody to attribute message content to them cryptographically. That's not so terribly important. But the other portion of the OTR system was the idea that messaging conversations go on for a long time. And so the idea is that when you send a message, that message you should not retain the decryption key on your phone to decrypt those past messages. And so the idea that was introduced in OTR was this notion of what's called forward secrecy, that after you send a message, the decryption key on your phone updates in some way, so that if somebody steals your phone, they can't read, or at least they can't decrypt off the wire all of these past messages. And this was implemented via something called ratcheting, which later became very important for the protocols that we use today. But really, the most important thing that happened in 2007. I don't need to explain this. It was the development of the smartphone. Smartphones changed everything. Smartphones took us from a world where we were using desktop computers and IRC and moved us over to a world where we have a portable device with a relatively powerful processor and memory and the ability to hold cryptographic keys, and created a world where suddenly we wanted to communicate with people using keyboards and electronically in a portable way. And that made messaging go from something that was this use case that only hackers on the internet really cared about with IRC to this mass adoption strategy where suddenly everybody was using SMS and other apps to communicate with each other. And again, this history is really well known, but I just want to repeat it. In 2011, Apple launched a service called iMessage. Now, iMessage we already talked about in the previous talk, but iMessage was revolutionary from a cryptographic perspective. It was revolutionary because it used end-to-end encryption natively, and it went out to millions, hundreds of millions of people in a single software update. The actual cryptography was pretty terrible. It was sort of an imitation of what PGP did. It uses RSA encryption plus some AES, and it uses a centrally hosted server to hand out encryption keys. That's operated by Apple. Lots of problems there that I don't love. But we're forgetting all the details. It actually turned out to be broken. We broke it in 2016. But forgetting the details of that, it took us from a world where encryption usage was measured in the tens of thousands at tops to a world where encryption usage was measured in the tens or hundreds of millions. And many of those people didn't even know they were using encryption. You pick up an iPhone and you see blue bubbles. That means you're using iMessage. But to the government, that's a massive change. A second thing that happened over this time period is that two inventors who the names should be pretty familiar, Moxie Marlinspike and Trevor Perrin, took that OTR protocol and they said, let's build an app. Let's build an app and a new protocol that's an extension of OTR, and we'll use that to do mass messaging. They renamed that to Axolotl, which was an awful name that everybody hated. And then eventually they renamed their protocol to the name Signal Protocol, and the app that deployed it first was called Signal, and probably most of you have that on your phone. And then later, in really kind of a coup, they were able to add the Signal protocol to WhatsApp somewhere in between 2014, 2016, and WhatsApp had 1 billion or 2 billion users. So the change in the number of people using encryption just was dramatic. And suddenly, this is not something that governments can ignore, which brings us to 2010, 2013 or so, which is what we're starting to call the second crypto wars. This is a website that is currently maintained by the FBI. It's been here since about 2013, and it's called the Going Dark website. You can Google FBI Going Dark. It's a beautiful branded website. They spent a lot of time on this. It was actually initially a priority of James Comey, who was the previous FBI director. And essentially what it does is it sets out, starting in 2013, that encryption is going to be one of the biggest technical challenges that the FBI has in order to perform its criminal investigation function. And it's really ambitious. It doesn't say encryption of messaging. It doesn't say encryption of phones. It says all encryption. We need access to encryption bypasses so we can access these devices and these communication systems. And without this, we will lose capabilities and we will no longer be able to protect the United States against everything. And keep in mind that the US FBI is, both a national security agency and also a criminal investigation agency. So they have both functions, and they care about the ability to break encryption as part of both of their functions. They also coined a term that they continue to use, which is called warrant-proof encryption. And they use this on their website. Warrant-proof encryption creates, in effect, lawless spaces that criminals, terrorists, and other bad actors can exploit. So none of this should be surprising if you've been following this debate, but this is the source back in 2013. We also know the history in 2015. Things came to a head here in the US where Apple had a phone that was used by a pair of terrorists, people who had conducted the shooting. The phone probably didn't contain anything. They had actually destroyed the phone that probably did contain information, but the FBI decided they wanted a backdoor. They wanted some way into this phone. Tim Cook said no. There was a huge fight. It ended in a sort of unsatisfying resolution when some technical folks, there was a story in the Washington Post this last week, some technical folks found a technical bypass that let them into the phone. So the FBI did not get to establish any kind of legal precedent, and Apple didn't get to fight them off and establish a legal precedent. The issue was just postponed. I also should point out that this issue is ongoing. This is from 2019, but I don't think this is an issue that has left anybody's priority queue. Of course, many governments all over the world have the same concerns about being able to access end-to-end encrypted messages. India appears to have a more unique problem, and I've heard this several times, which is that not only do they want kind of the same investigative capabilities, the ability to access plain text and so on, but they also want to track the forwarding of messages, particularly on WhatsApp, because of course there have been a number of incidents. And so this is a really unique requirement. It doesn't come up very much in the US debate, but it's very, very specific to India. And it's a little more tractable, but it's something I'm just going to talk about a little bit later. Going back to the United States, of course, we have seen legislative proposals that try to add these capabilities of being able to decrypt information. There was recently one that happened in the middle of last summer where a group of US senators introduced a law that basically said more or less what Joe Biden said back in 1991. If you operate a service, you had better be able to give us plain text. The bill didn't pass into law, but it shows that there is a pretty strong interest in continuing this kind of legislation. Nearly done with this history, but I should mention that the Five Eyes governments, including as well as India and Japan, have all been combining and joining forces on asking for encryption backdoors and more, which I'll talk about in a second. So again, this is not just an isolated series of governments doing what they do, it's all over the world and it's in coordination. Okay, good. So now I've said all these things and I want to talk a little bit about what governments are actually asking for, because I think it's a little bit complicated and I don't think even governments fully understand what they're requesting. So let's be clear. When it comes to messaging, and I'm going to keep this entire talk on the subject of messaging. When it comes to messaging, what they're looking for, obviously their preference, is the best kind of encrypted messaging service is one that doesn't exist, one where the messages are not encrypted. They're sent in plain text and they're retained in long-term stores at providers. So a warrant, police can show up and say, give me all of the messages sent between these people, and the problem is solved. That seems to be a very, very strong desire, or at least if we don't have no encryption, we can slow down the deployment of new encryption. Failing that, there is a strong push to develop what are called key escrow systems. And of course, this is a very technical group of people, I think, but just to be clear, let's define this. Key escrow means that every time we send a message, we're going to have some master encryption key, which could be held by the government, although the US does not seem interested in holding keys, but more likely held by the provider or company like Facebook or Apple. And that master key will decrypt on demand whatever message needs to be decrypted. And that seems to be the general push. I just want to stress here how scary that requirement is, right? So if I have a master key sitting somewhere that can decrypt criminals' messages, then there's nothing technically to prevent that same master key from decrypting everybody's messages. So if that key is stolen, everything is clear text to the person who does steal it. This is a very, very strong requirement. The more interesting current request that is actually getting a lot of traction, I think, unfortunately, in the United States, is actually kind of a very hard shift. So governments have mostly been asking for the ability to what they call get exceptional access, gain access to messages when they have a warrant, which and the exceptional means, no, this is not the normal case. We don't want to read your messages every day. We want to show up with a warrant. It will happen very occasionally. It will be the exception to the normal message flow. However, very recently, an entire group of governments, particularly here in the US, the Attorney General, signed on to a new requirement that comes kind of out of nowhere for us. And it basically demands that we have real-time content scanning. And the idea here of real-time content scanning is that we can look at every single message that you send through the system, and we can check it for certain properties. And the most common property that's mentioned in the US is this an example of what we call CSAM, or child sexual abuse media? And it's a very powerful request because none of us, I mean, I have kids, none of us wants this to exist. None of us likes the idea that this kind of media is flowing through systems. And of course, the idea that end-to-end encryption can facilitate the transmission of this kind of media is horrifying, and it brings out an emotional reaction in everybody. But from a technical point of view, it's really important to understand the difference in the requirement, in the ask, what governments are asking for, between asking for exceptional access and asking for real-time content scanning. The first is an exceptional capability that is not used except in occasional, very serious legal instances when a court has granted a warrant. The real-time content scanning is a ubiquitous workflow. Every single message is being checked. Maybe not every message is being flagged if the system works well, but every message is being scanned. And from a technical point of view, that's a very, very big difference. There are some governments who I think are being a little bit more reasonable in the sense that they're asking for more targeted wiretapping and eavesdropping. The UK has made a proposal for that, so that's a little bit more reasonable. We'll come back to that in a second. One of those is called the Ghost Users Proposal, which GCHQ in the UK came out with. And of course, I mentioned previously traceability. This is kind of the new one for me. Very hard, and we'll talk about, well, potentially hard, and we'll talk about why that is in a minute. So I don't want to spend a ton of time on key escrow because I think most of you really kind of do understand this, but I want to present it from the government's point of view, which is kind of, this is what the governments want. They don't care about key escrow. They don't care about key storage or any of the details. They basically have been demanding, at least in the US, that companies should be able to produce plain text on demand. It's interesting because in the 1990s, when Clipper was the proposal, that system was actually very, very carefully developed so that US agencies, US government agencies would hold keys, the master keys. There would be a process to split the keys across multiple agencies, and everything was done centrally by the government with certain protections in place. The various proposals that have been made recently do not include that protection. They basically say, hey, you figure it out, industry, go off and figure it out, which means, of course, you can imagine Apple, which is very well funded, could probably build something more reasonable. But you can imagine there are a lot of other companies, very small companies, that are going to be figuring this out from scratch, who are going to do it very poorly. And so this is not necessarily an easy ask. So, obviously some of those companies will say, well, we just can't afford to do encryption at all if this is the requirement. That's a very likely outcome. But generally speaking, what it means is that somehow they're going to have to encrypt session keys for messaging using some kind of escrow key. That key is going to be stored somewhere, typically on a messaging provider's hardware security module. And we're not really sure how they're going to do that. That's a very, very hard thing to do. And we know this is a hard thing to do because the US government tried to do it once, and the result was the Clipper chip. And it was broken, not necessarily in its key escrow function, but it failed its design, which was created by the US National Security Agency, had a field with a 16-bit message authentication code, and Matt Blaze at Bell Labs was able to figure out that he could bypass the encryption, the key escrow function on this chip relatively easily. And partly as a result of that design failure, support for this kind of government-designed key escrow collapsed. Now, this is the US National Security Agency. Whatever you may think about them, they're supposed to be good at designing encryption technology. So the fact that they failed on that aspect of the Clipper chip was a good indication that maybe this is not such an easy problem to solve. So key escrow in the US is not very easy to do. And of course, we couldn't have done it. It would have really been very bad for software security and so on. We also had a really interesting example of how bad key escrow could go wrong, even if you protect the master keys. I like to cite this to government officials, at least here in the US, because none of them have heard of this. But many of you, or some of you, may have heard that in the 2000s, this came out during the Snowden slides, The US government created what we believe to be a backdoored pseudo random number generator. It was called dual ECDRBG. And there's a long story I'm trying to cover very quickly, but we believe that this algorithm had a covert backdoor, and it was put out in NIST standards. And for reasons we still don't fully understand, this algorithm wound up inside of Juniper NetScreen firewalls in about 2008. And they continued to be there through about 2012, and actually 2015 and so on. In 2015, a group of non-US hackers, we believe, possibly the current rumor is possibly Chinese state-sponsored hackers, were able to get into Juniper's NetScreen code base. And what they did was really alarming. What they did is they took this possibly backdoored algorithm and they replaced a single 32-byte field with a key that they had generated themselves. We don't know how they generated it, but clearly they did this for a reason. And what we know about that, in fact, we did some of the research just to verify this. What we know is that this creates an opportunity for anyone who has the corresponding secret key, in other words, the hackers themselves, to decrypt any VPN connection that was made by these firewalls. And so essentially they took our backdoor, and by R, I'm being very specific, the NSA's highly likely backdoor, and they turned it into their own backdoor. And I think this illustrates kind of the risk. There are so many risks around key escrow systems, and dual ECDRBG is one. This is an example of how dangerous they are. You cannot hold these systems against very sophisticated state-sponsored attackers. And this kind of shows us one of the possible outcomes. I don't want to praise other backdoor approaches, but in a few years ago, GCHQ in the UK came up with their own approach. And I'm not in love with this, but at least it gives you an idea of what's possible. GCHQ proposed an alternative approach to creating some kind of backdoor into messaging systems. And what they identified is really valuable. They pointed out that most messaging systems have a server, and that server's job is to, when I want to talk to Bob, I go to the server and I say, give me Bob's public key. And this is called the identity subsystem. Really, its job is to hold on to who's part of the system, as well as their public encryption keys, and give them to me when I need it. And all of the systems that we're familiar with have a server like this. Apple iMessage, WhatsApp, Signal, they all centralize this server to distribute public keys. And when you go and you try talking to a new user, you're trusting that server to do the right thing. You're trusting it to be not compromised. Most systems have some kind of key fingerprints. You can verify that, but nobody does. The idea that GCHQ proposed is, well, here's the weak point in all these systems. Let's attack the weak point. And what they want to do is they want to subvert that identity management system. They want to subvert that server to insert either wrong keys or add new users. So when I try to make a private conversation to Bob, it's not just me and Bob. It's me and Bob and maybe the FBI. And this seems very simple. Of course, then the question is, why doesn't my app tell me that the FBI is present? But of course, the problem is that they're also proposing that we change the app so it doesn't reveal facts about who is part of the meeting. Once you start doing that, pretty much anything's possible. But I will give GCHQ credit, at least in this case. What they've identified is at least a system that does not have the same vulnerability as the key escrow approach. If you steal the keys from GCHQ, you won't be able to decrypt anyone's message. You'll have to actively target a particular user, and that's not always so trivial. So this is at least a slightly lighter approach, even if I think it's unworkable. Okay, I want to briefly talk about tracing, and I think what's kind of notable about this part, this idea of tracing different people's text forwards or attachment forwards, what's really notable about the problems in tracing is that it's just a problem we don't quite know how to solve. So here is an article that talks about a government, Indian government proposal to do some kind of hash-based tracing. And I think the idea is basically if somebody's forwarding an attachment and it becomes very, very popular, we can find out who started this, or we can go back and see the path by which it arrived at being viral. The government in India has proposed some kind of hash-based tracing. I've seen some research that proposes other ways to do this. It's possible that WhatsApp already has some way to track forwards. It's a little bit difficult to tell. But it's not necessarily the case that we know how to do this, because the situation is sort of fluid. Um, some people have proposed tracing approaches that are privacy preserving, in that you can only trace messages if they achieve large scale virality. But the problem is, we don't know when a message is just starting out. If an attachment is sent out from one person and it reaches 10 people, and then it goes to 100 people, and it goes to 1 million people, at what point does it become traceable? Is it always traceable from the point where I send it to my 10 friends? Or is it traceable at the point where it reaches 1 million? And then somehow when it reaches 1 million people, can we go back in time and identify who sent the original 1 to 10, et cetera, viral push? And so these problems, I'm not saying these problems can't be solved. I'm saying we need a lot of research to really figure out what is being asked for, if we don't want to just build a system that traces everybody's messages everywhere. And this is kind of an example, I think, of what governments are asking for. I'm enthusiastic about solving problems. I am uncomfortable with the idea that governments are saying we need a system today, when we researchers don't even know how to build that system. That is just generally one of my concerns. So I think this is largely a research problem. I believe I have about 10 minutes to leave time for questions. So I want to talk about another issue, another area that really, really concerns me. And this is a place where I also believe that we are just at the research stage and governments are demanding that we deploy systems. This is an area where I'm actually really deeply concerned that we're about to make a terrible mistake. And this is the area of real-time content scanning. I'm pointing you to, this is the US Department of Justice press release, but actually it's not just the United States. It was a joint release that was made with a bunch of Five Eyes countries as well as India, that talks about how we need to build real content scanning systems. This was signed by William Barr, who is the Attorney General under President Trump. And this basically says, we need you, Facebook, to stop deploying encryption systems unless you can build real-time content scanning systems so that we can prevent sexual exploitation of children and so on. And there's a very noble and very good motivation, but I want to talk about some of the issues with that. Again, the motivation in the US is mostly child abuse, sexual imagery, or child sexual abuse imagery, which I'm going to refer to as CSAM over and over again. So if you don't know what that is, CSAM is horrible stuff. But there are also other proposals for terrorist imagery and other things like that using the same technology. So we won't be too specific about it. So let's talk about kind of where we are today. And I'm going to come back to the CSAM debate. Before we get to CSAM and how that's a problem, I just want to kind of give a quick update in where we are amongst the technical and policy wonks. And these are not just the pro-encryption people. These are also the national security wonks here in the US, as well as other folks from the UK I know have weighed in on this. I think that we are approaching a growing consensus that end-to-end encrypted key escrow for messaging specifically is not a great idea. And I think this is a reluctant agreement, because I think that the policy community has started to get the idea that we don't know how to do this safely, and that the attackers who will be after these keys are just too powerful. And as evidence for this, I would give you a report that came out a couple of years ago called the Carnegie Institution report on, I'm not sure what the title is, end-to-end encryption and how do we deal with the national security debate. And what they concluded is that in the setting of physical devices like phones, key escrow could work. And they argued that specifically in the setting of phones, decrypting phones, this could work because in order to do surveillance on somebody, you first have to get their phone. And so the idea of building a key escrow system and allowing for mass surveillance, if the key escrow system is compromised, it's very hard to do that against phones, because first you have to get my phone. Whereas with messaging systems, what they call data in motion, the data, all you have to do is compromise the right server and you can get access to millions of people's messaging, which means that key escrow systems could very rapidly lead to mass surveillance. And so there is a sort of an agreement, a reluctant agreement, that this is not a great approach. And so, as we've noticed, a big shift has been to move towards a push towards content scanning as kind of a new ask. And so what we're asking for now is real-time ability to scan for CSAM material. But of course, the implied compromise here is that these systems will be built only to scan for abusive content. Yes, every message you send through an encrypted messaging system will be scanned, but only to see if it's child sexual abuse material, not to see if it's a criminal message or if it's something that's politically charged. And it's also a very good political way to bring the debate into an issue that people really care about. The biggest problem with this area, the content scanning area, is that we, meaning the technical community, has no idea how to build it with end-to-end encrypted messaging. I've had recent calls with folks from Google who said, we really want to build this. We really believe in content scanning. We think this is good. Can you tell us how to do it? And nobody knows. Researchers are still thinking about it. And, there's doing it, and there's doing it safely, and those are two different issues. So this brings me to this list of things that governments are asking for that we just don't know how to do, which is obviously build safe key escrow, do content tracing, and content scanning, which is essentially everything that we're kind of being asked to do. So we moved from a world where we don't know how to do something just safely to a world where we literally just don't know how to do it at all. I'm going to kind of skip past, just in the interest of time, I'm going to pass. I think I've said enough about key escrow, but I want to briefly finish up for the next 5 minutes by talking about content tracing and how, not content tracing, sorry, I'm going to skip that, content scanning and what the problems are with content scanning. I want to just show you how content scanning works today in an unencrypted system. So this is an illustration. I've used Facebook as the example. When you send a message through Facebook Messenger, an unencrypted message through Facebook Messenger, what's happening to that message is it's being sent to Facebook servers in clear text. Obviously, it's probably TLS encrypted, but it arrives at the server in clear text. Facebook then uses what's called a media hashing algorithm, which is a fuzzy hashing algorithm or a fingerprinting algorithm to generate a hash. And then what they do is they check that message against a hash corpus. And that hash corpus is a list of, I think, 14 million abusive images that they keep and constantly update. If the message doesn't trigger, if it doesn't get a close match against any of those hashes, they send it on to the client. If it does trigger, then a bunch of things happen. That person's account may be investigated. The image is going to be manually examined by folks at Facebook. It's going to go to an organization here in the United States called NCMEC, which is the National Center for Missing and Exploited Children. And if the sender is a US user, they will hopefully be arrested. If they're an international user, pretty unlikely, but that's kind of the process today. And of course, these media hashing algorithms, a very famous one is something called photo DNA. And it's a fuzzy hashing algorithm because the idea is that you can't use SHA-1 or MD5 to match these files because people have different encodings of the same file, like a JPEG and a GIF or a PNG will have a different hash, even if they're the same image. So these fuzzy hashing algorithms look at the way an image works. There's another model that's coming up right now, which is essentially a system which uses a neural network. Google is starting to deploy this. Of course, we know how neural networks work. You can train them on large numbers of images, and they will trigger if you've passed them a new image that has the same features. And the nice thing about this approach is we can identify new images that trigger the neural network instead of just finding a list of existing images. And so Google is starting to deploy an API for this. But again, their system relies on the idea that the messages reach Google servers unencrypted, and then they can be analyzed by this neural network. Okay, so this is the basic approach. Now, I want to just very briefly identify some of what we care about, security considerations. All right, so first of all, we require in these systems that the server has to see the media to process it. In these existing systems, end-to-end encryption is not possible. The scanner has to have some kind of hash corpus or algorithms or maybe a trained neural network that can do this. This data is intensely proprietary because, I'll show you why, but in the hash corpus setting, if you get access to those hashes, sometimes you can reverse them back into very, very low quality pictures. So if I give you a hash database full of abusive images, the last thing I want to do is reveal that information to you. So that's very bad. And in the neural network case, it's much worse. It's possible in some cases to actually pull images out of a trained neural network. And you've seen this before, probably if you've ever looked at these kind of neural networks. You can grab imagery out of a neural network. And the last thing we want to do is make one that's trained on abusive images public. Criminals who have access to the model, direct access, can easily bypass it. They can develop software that takes any image and make sure that it will never trigger the network. And similarly, providers and third parties now can do abusive things. They can, instead of just training their model on abusive images, they can put political images into their models. And they can take legal speech, and they can now have a system that triggers on that speech as well. Now, just imagine, forget about providers being malicious. Just imagine that a group like 8chan was to get involved in creating imagery that got into this model. Imagine they wanted to cause problems with these models. This is any system that is vulnerable to 8chan griefing the system is not a system you can deploy. So these are very bad things. I'm just going to very, very quickly kind of skip over some of these slides, but we remain in a world where we don't know how to do this kind of model evaluation or hash evaluation on encrypted data. Most of the techniques we have require some kind of multi-party computation or fully homomorphic encryption. We can use a variety of different techniques, but they're all fairly inefficient. And they also have problems with this question of what if the provider has a database that has images that we don't trust. If the thing that we're evaluating is a neural network, we actually have some results that tell us how efficient it is to evaluate a single image against a neural network. And these are small images. It turns out that some of the best systems we have take hundreds or thousands of megabytes of communication to do a two-party evaluation of one image against a neural network. So the technology is just not ready for that. We need more research. And on the question, which I think is probably the most interesting research question, if we're going to do content scanning, how do we stop this from turning into a panopticon? How do we stop governments from using this to essentially turn it into a spying system against end-to-end encryption? And we just have no idea how to do that. How do I know that the system isn't scanning for anything that an abusive government wants to scan for, or maybe somebody, some inside attacker inside the provider wants to scan for? The answer is we just have no concept of how to do that. If we want to deploy those systems safely, we have to build a system that can actually guarantee that what's being scanned is something, the database is something that we trust. And if we don't do that, if we can't build that, how can we possibly deploy these systems? The only possibility is to build basically the largest mass surveillance system that any democratic government has ever built. And we just don't want to do that. So there's a lot more research that we need to do. And it seems like I'm out of time, so I'm going to very fortunately reach the end of my slide. So thank you very much. And I hope some of that was helpful, and I'm here to answer any questions you have. It was very nice to be here. Thank you.
Hey, questions are now open. You can use the QA tab and post the questions. I'll just read them out, and Mr. Brain will keep answering them. The first question is from Sumankar. He asks, assume key escrow is in use. In case FBI pursues the case, don't they have to share the master key during discovery phase?
So the current approach that I've seen given and proposed is that a provider, and here I'll say Apple, will store the master key, and a message goes through the network, and or maybe a group of messages, and the FBI comes and says, we need all messages sent by this phone number at a given time. And at this point, Apple is permitted to use its master key to decrypt only those messages and turns over the decrypted messages to government and doesn't have to reveal the master key. That is at least the way the United States is trying to offer a guarantee that this won't result in mass surveillance. That's the proposal that I've seen. And so hopefully, no, we don't have to reveal the master key.
Okay, the next question. NISP is holding a lightweight cipher competition. Will IoT devices be able to implement the standard algos faithfully, and B, does crypto add enough costs to discourage OEMs from implementation? Yeah,
I mean, at this point, anything that we do to I mean, of course, IoT may not have to do end-to-end encryption, but actually it is, right? So my phone today uses a variant of Apple iMessage to do, and I think we talked about this in the last session, to talk to other devices around the house. They want to do end-to-end encryption. Anything we do to add key escrow is going to significantly increase the weight and the complexity of the protocols that we have to build. And this is definitely not something we want to do in areas where lightweight crypto is required. So it's another disadvantage of these approaches.
Okay. Third question, FBI dropped the child porn case because they didn't want to disclose what is called network investigative techniques. which reveal people's identities. Do you have insights into this technology? Does this provide a good counter argument to breaking E2E?
Yeah, this has been interesting. So there is, I think when people talk about NITs, what they're talking about is browser hacks or phone hacks. And this has been, to some extent, the way that investigative agencies have bypassed encryption in the past. They give something that is a JavaScript vulnerability in your browser or some kind of drive-by vulnerability in your phone. Their argument is that this is too expensive and too unreliable for them. So they still want surveillance, they still want encryption, key escrow, and so on, because they think the costs are too high of using hacking and it's not going to be sustainable. However, the evidence is pretty good that it's worked well for them so far. And of course, there have been these kind of proposals. People have said, hey, we will allow hacking if you agree to drop key escrow. But that's not how negotiation works with the government. They may ask for key escrow, but there's no quid pro quo, right? We're going to end up with probably hacking and key escrow, and so that's the thing we need to keep in mind.
Shai Kitris asks, how would the Israeli NSO hack into E2E encryption? And
Yeah,
he's asking this in the question of context of WhatsApp.
yeah, obviously, very good question. NSO does exactly this. They make zero-click. Now they're zero-click attacks. They used to be one-click attacks. Now they're zero-click attacks on things like Apple iMessage and other kinds of apps. And they're really good at this. But it's not cheap. It's very expensive to get an NSO exploit and target somebody. The real downside of end-to-end encryption is that it's only secure if the ends are secure, right? The idea is that this phone is one end of the communication and your phone is the other end. If you get this phone, then you have the plain text. And so a lot of these NSO type exploits, they get access to the phone. They are then able to basically dump the entire WhatsApp plain text message database, and you're done. Now, what I will say about that is some of the uses of NSO have been kind of abusive. You've seen NSO exploits used against journalists in some countries in ways that clearly do not seem like reasonable law enforcement. However, what I will say about that is at least the number of cases of this has been fairly minimal. Whereas if you talk about something like key escrow, you really have the capability for mass surveillance, and NSO style hacking at least limits that kind of mass surveillance somewhat. So that's the benefit of living in a world where NSO exists, only NSO.
Next question. Currently, India is attempting to govern messaging apps through collecting the originator of specific messages that they deem affect the sovereignty of the country. In such a situation, how do we ensure that individuals or specific groups are not targeted? How can we reduce algorithmic bias in such a situation?
I don't know that there is a way. I wish I could tell you that there is a way. I think at a certain point, right? I'm a generally politically very distrustful person, but my observation over my lifetime is that once you have the capability to do this stuff, whether it's intentional or not, some kind of bias will creep in and you will see these things abused. They may be abused by a small number of participants in the system, but they will be abused. And the only way to prevent that kind of abuse is to stop these targeting, any sort of targeting in the first place. I'm not saying it's a perfect solution, but that's all I can offer.
Any other questions? Yeah, okay. The client-side operations, which will be performed for content scanning, could be spoofed by having a malicious device which is something else and input something else. How will this be solved?
Yeah, so some of the proposals right now, and I believe Snapchat may be deploying this, is I push the hash database down to your phone, and then your phone has a copy of it and then checks. And of course, this assumes that I haven't jailbroken my phone and I haven't hacked Snapchat. Of course, if I do any of those things, then I can just disable content scanning and there's nothing the provider can do about it. So this is a big weakness, and you have to imagine that people who are very serious about using these systems to deploy illegal content will figure out how to deploy a jailbroken Snapchat app. So this is a big weakness in these systems. Again, I think the best thing to think about here is that these content scanning systems, they're not designed to work against people who are very smart. They're not designed to work against the kind of people who attend this conference. They are designed to scan and to catch people who are non-technical and who are dumb enough to send their content through an app that is well known to have scanning and not to do anything to evade it. I think that's how governments are thinking about this. They're thinking that's good enough. But you're absolutely right. From a technical perspective, it's a very hard problem to solve.
Suman asks, Facebook paid a cybersecurity firm 6 figures to develop a zero-day entails in order to unmask a man who spent years extorting children. Do you think this is a fair compromise to catch hold of offenders without breaking encryption?
I mean, I would, if the alternative is mass surveillance, I would much rather that's how things are done. I mean, it's, this is a place where we're going to have to find a balance. We have to find a balance between catching the kind of people who do things like that and building a system where there is no protection for anybody. I think that once we make the compromise of there is a master backdoor, that compromise, we can never go back from it. It is something that is going to expand and the usage is going to leave our control. The only control we have is, do we have the ability to say no to that backdoor and then revert to targeted approaches like what you just described? I'm a little dogmatic about that, but that's how I feel.
Okay. Any more questions? Okay. Do you foresee a possibility at all that CSAM and such beneficial content scanning can be affected through processing on client devices instead of delegating to a server?
Yeah, I think it can be. There are some downsides to it. Here's the biggest downside, just from a technical perspective. In the case of photo DNA, which is the hashing algorithm, my students and I have been looking at this algorithm to see whether it can be abused, and we can't. We can't do it because photo DNA is secret. Microsoft owns it and will only release the algorithm under NDA. Now you have to ask yourself, why is Microsoft keeping a hashing algorithm secret? The answer is because they don't trust it. They think that if they reveal the technical details of that hashing algorithm to the world, it will be broken and people will figure out how to bypass it and or trigger it on non-malicious content and all of the bad things that can happen. That to me indicates that Microsoft and others are not very confident in the robustness of this technology. They're relying on security through obscurity to keep it working. Now imagine a world where we put photo DNA inside of every app and the code is there and anybody can reverse engineer it and take it out. Does photo DNA still work in that world? I don't think Microsoft knows. I don't think anyone knows. And that's a concern for me.
Okay. Any more questions? Oh, we have some more time for Mr. Green. I'll wait for 5 seconds and start. Any panelists? Panelists who are already there, you're not free to ask questions directly. Renal? So, no, he's not there. Any more questions? Okay. All right, I'll ask a few then. Is it possible for satisfying some of the intelligence agencies' requests by using metadata from messaging apps?
I think so. Yeah. I think that metadata reveals a lot, and I think that currently is being used to a great effect, right? We have the NSA has a line in one of the Snowden's lines that said, we kill people based on metadata, which is not a great thing. I'm not endorsing that. That's awful. At the same time, they're able to come to enough confidence that they can perform military options based on metadata. And I think metadata leakage is a huge issue from a privacy perspective. It reveals a lot about what you do. The problem here is that this is a world where having more information is always better. If metadata works well, but having the content of data would work even better, then you're always going to feel pressure for people to get the content too. And it's an inexorable, there's no compromise that anyone will be happy with in this world, unfortunately.
Okay. You had also mentioned about the Carnegie's encryption working group paper, which basically said one of the paths that one could take is go for the cell phones and not touch data at motion.
Yes.
Is that a viable alternative, at least in terms of resolving the standoff to some extent?
I wish that we had gotten there. I thought we were resolving in that direction. I thought we were resolving in the direction of hardware only and data in motion is a problem for some other day. However, the content scanning debate really undid some of that, because not only is it inherently data in motion, because we're talking about messaging with content scanning, but it's such a powerful requirement that we need access to every message, just to scan it, but every message, that it really turns the debate upside down. It seemed like we were getting to a place, and now everything is thrown apart. So we don't know what to do.
Is there anything that you want to add upon Ray Ozzy's proposal of burning the hardware chip that just blows up? I mean,
yeah, I don't love it. My big objection, by the way, Ray Ozzy has this proposal where he says, we can have phones that, like, there's a master code that you can enter into a phone which will unlock it, but there's a protection, which is there's a hardware chip that will burn a fuse or something when that happens. So you'll at least always know. There's no way to scan somebody's phone without them having a dead phone. And Ray Ozzy bases this on the idea that we can build secure hardware into phones. I would comment that we've spent a lot of time trying to build secure hardware in phones, and we continue to fail. And up until very recently, there was a major vulnerability in Apple's secure enclave processor, which is the main hardware processor inside of phones, that was allowing people to brute force passcodes, which they should not have been able to do. So I love Ray Ozzy's idea. I'm skeptical that that mechanism will work as well as Ozzy thinks it will. And I just want to make a plug for some research we did. If you go to securephones.io, my students and I spent last summer writing about a 110-page document on everything we know about security mechanisms in existing Apple and Android phones. It's not complete, but if you want to learn a lot more about how well this hardware works and what Apple claims it can do, that's a great place to go, securephones.io.
So Shubham Jao asks, while the keys used for encryption of the messages are different, can using a cipher blockchaining mode like ECB for encrypting end-to-end messages help detecting patterns of messages and correlating cipher texts?
Yeah, I think that the encryption modes right now are all pretty good at doing what they have to do. And I see. So I think you're saying, can we make the encryption weaker? Is I'm just trying to understand, so that we get leak some data, or just trying to, Apple does have these deterministic, they call them convergent encryption modes, where, if you encrypt the same message twice, then you get the same ciphertext. That could leak some information, but that sounds awful to me, right? So every time I say, okay, we're going to leak some information that is recognizable, that seems, I don't like systems that use technical weaknesses to make to solve policy problems. I think at the end of the day, we have to tackle this head on and say, look, what does government want? How reasonable is it to give it to them? And then let's build the system that does exactly what they want. Let's not let the cryptography dictate what policies we are going to build. Let's build the policies that we need to build. And so generally speaking, I think leaking data deliberately is not necessarily going to satisfy anyone, and it may be actually very harmful.
I had a question on your paper, 110 page paper. So one of that is, is it possible, is that how Celebrite and vendors use it for hacking phones in general? When they talk about doing before boot, after boot kind of a model?
Yeah. There is this notion, just to repeat for everyone, there's this notion of before first unlock and after first unlock, and I think that's what you're asking about, which is, when you unlock your phone, a bunch of encryption keys stay in RAM and they don't necessarily go away. Everything that we did last summer was to try to answer the question of how Celebrite is getting access to data. Do they have some way of breaking encryption, breaking the secure enclave processor in Apple phones? And the answer is, as far as we can tell, that Apple encryption is just very weak. Once you have an unlocked phone that's in the after first unlock state, the keys are in RAM. If you can get past the PIN code using software techniques, if you can get past the software protections, then you can get access to data, and there's very little encryption on the phone. So that's our theory. Is right now that's how Grayshift and Celebrite are getting access to phones.
There are a couple of questions on YouTube. So just let me just go mute it and then go find them. David, I couldn't find the YouTube link or questions on it. Will you be able to find it and paste it? Okay. So the questions are backdoors a means of accessing by themselves, for example, introducing vulnerability through software updates? Is this different from PSCO?
Yeah, introducing vulnerabilities to software updates is a huge problem. One of the problems we have right now is that all of this end-to-end encryption assumes that we trust the client software. You trust the endpoints, you trust the client software. If you don't trust the client software, things are very bad. And right now, we live in a model where Apple and Google and WhatsApp, we trust them to push honest software, but we assume that governments can show up and demand plain text, but they can't force them to push software updates. This is not a world we really can live in, and the best techniques we have to prevent that are things like open source and reproducible builds. But even there, we don't have perfect solutions. And I'm very, very nervous that we'll move into a world where that is a common technique for governments to attack software update systems and push malicious updates, and we won't have good defenses.
The next question is by Anand Chittiputu. He asks, the content filtering for CSAM can be easily bypassed by adding another layer of encryption to the shared images. Yes. Am I missing anything here?
Nope, you're not missing anything. It's like I said, if you are determined to get your data through these systems, if you're technically savvy and you're even mildly technically savvy, they do nothing. And I would also add that many of these content scanning systems here in the US, Facebook, 97% of the hits that Facebook's hashing algorithm records, 97% of them are outside of the United States, and a vast number of them are basically beyond any sort of law enforcement response. So most of what these hashing algorithms do is they allow Facebook to detect and shut down accounts. They don't even have a major impact on the actual production of this kind of media. So yeah, I think one way you can look at this is you could say that this is designed to catch the low-hanging fruit of people who are technically incompetent and are not very advanced. The other thing you could say about these algorithms is that they don't work, is that they're not stopping people from sharing this material. The material is being shared more than ever, and people don't care about being caught. They don't care enough to encrypt their files before they send them through Facebook Messenger, simply because there are so few consequences to them. These approaches just don't work very well. So it's sort of like if you have criminals running around in broad daylight, then the problem is that maybe your laws and your police aren't working. I think that's one way to look at this right now. Yeah, you're right. You could bypass them, and people are choosing not to.
Okay, we have a few more minutes. Any other questions to Mr. Green? You can use the QA tab or put it on YouTube. Okay. What type of policy is essential to combat the large-scale surveillance that governments are attempting to implement? As you said, you need the policy to define the software.
It's very hard. Yeah, no, this is a hard problem, and I wish somebody would solve it, because this is what we need to do before we deploy things. One of the things we need to have some sort of notion of what is it that we want. So for example, one policy might be that we can absolutely decrypt some data under warrant, but we need to be able to publish the number of such warrants. I mean, that at least would provide some immediate visibility into whether there's mass surveillance or not. It's very hard to do that, enforce that technically. Other policies we might include are that the warrants have to be digitally produced, and maybe someday they become public. That's not something that police are very comfortable with right now, but that might be something we could do. Again, and if we're moving over to the CSAM detection world, then the question is, let's say we have a database of CSAM imagery or alleged CSAM imagery. Who's verifying it? Who's checking that those images are actually CSAM images? It's not something you can just release to the whole world to verify. Do you have an agency that is widely trusted, who checks that what's going into that hash database or that model is actually what you expect it to be? There need to be systems in place to do this, and we just don't have any idea what those systems look like.
Okay. 2 more minutes. Any other questions? David, are there any other questions that came on YouTube? You can just paste them here.
No, that's all on YouTube.
Okay, one more minute.
These have been really good questions, by the way. So don't feel bad if you're not giving any more. This is great.
Okay, I have two last questions, and I will let you go after that. So here is my difficult question for you, not really encryption, but about policy. What if, so the first question is about Signal. Do you really think it's a good idea for Signal to use, to bring in payments, particularly cryptocurrencies, into its product line, given that the governments are much more hostile to cryptocurrencies, as it is they're much hostile to encryption, E2E, and bringing crypto means all this stuff about money laundering and all that kind of stuff? Do you really think it's a good idea?
Yeah, no, I think it's a very bad idea. I want to just comment here, full disclosure. I co-invented Zcash, and I have a little bit of a conflict here because when you talk about payments, everyone will say, hey, it's he's talking about his own currency that he helped invent, and that's true. I do want to say this though, which is that Signal is a very clean encrypted messaging story, and it is a target of governments, and they want to shut it down. They would use any tool in their arsenal to shut it down. And when Signal is using a cryptocurrency that is some pre-mined cryptocurrency that's also private, they are moving out of a world where we can say, look, it's just messaging and it's protected by the US First Amendment and this and that, to a world where suddenly they're doing very different things. And I think it's not a good place for them to be. It's not a safe place for Signal to be. And I really wish they weren't doing it. If they went ahead and released a currency and just put it in another app, that'd be great. It's putting it in Signal that makes me nervous.
Last question. What if governments actually put a gun, like in India, what has happened is that they're basically saying, if you're not complying to the rules and regulations that we're asking you, we're going to put your executives on jail. Do you really think it worked in any other place before?
Any place can reach that point, and it's not so far. The argument I've made in the US is if you pass legislation that lets you do that here in the US, then the people will move overseas and you'll start seeing encrypted messaging apps out of Switzerland or India or wherever. But it's possible we wind up in a world where every government does this. And I'm not sure what the answer is. Maybe it's some kind of decentralized system. It certainly won't be good for anyone.
Okay. I think we have answered everything. Thank you, Mr. Green, for your time. Nice talking to you.
Nice talking to you too. Thanks very much. Good questions.
Thank you.
All right.
Right. Rishan, the next session, if it was merged around, can you invite your panelists to have a bunch of announcements to make? Okay, it was merged around. All right. Yeah. Hi. Okay, so we have an interesting session which will be held slightly differently. I will just read through what the session is going to be. Uzma here is going to present a session on how they implemented live location on WhatsApp, and also some interesting technical details about the Diffie-Hellman and the ratchet algorithms. Just to reemphasize, this is a session that is held under, is actually a beta feather, but